In this video, we're going to discuss a very important general chemistry lab technique, titration volumetric analysis, or more simply just titrations. Suppose that we have a solution and we know it's acidic, but we don't know how much acid is in there. We don't know the concentration of acid or H+ ions. That's an important thing to know. How acidic is my thing? Now, litmus tests with litmus papers can get us to a close range, but let's say that we need to know really exactly how much acid we have. Well, a titration can tell us this. And before you think it's just something you do in chemistry lab, one of my previous jobs before I was an instructor and science teacher was working in a wine lab in Napa Valley. And wine is acidic, and as it ferments, it changes how much acid is in there. And the amount of acid really affects the flavor and the fermentation process. So my job at the winery was to go collect samples of the fermenting wine 3 times a day and titrate that wine, titrate that unknown amount of acid to figure out really exactly how much acid we have. I went to the winemaker, told her those numbers, and then she was able to make adjustments to the flavor and fermentation process of that wine. So it's not just in chemistry labs, it's in real life too. So let's go ahead and talk about how we set up a titration and why it's important to know how to calculate an unknown amount of acid. So we have here a schematic of a titration setup. You have to imagine that, of course, we have clamps here holding this long burette in place, but we'll have a solution in our Erlenmeyer flask. And this is our unknown. This is where we know it's an acid or a base, but we don't know how much. Now, I used the example of an acid in the intro to this video, but it can be either. It can be an acid or a base. So an unknown molarity, all right, so that's the moles per liter of an acid or a base. And this is called the titrand, A-N-D, which we'll go ahead and put in pink. So that's how we're saying, hey, this is what we have that we're interested in figuring out how much acid or base we have. Now, it's important to know that we do know the volume, all right? So the volume of our titrand is known. That's an important part of our calculations. How do we know it? Well, it's however much we put into the Erlenmeyer flask. So in my example, when I was working in the wine lab, I would take 100 milliliters and I would measure it out and make sure that I had exactly 100 milliliters in my Erlenmeyer flask so that my calculations would be accurate. Then we put a known amount and a known concentration of the opposite. So if let's say for our example here, we're working with an acid. If we're working with an acid, we're going to fill our burette with a base. So we're going to have a known concentration of our base or acid. So the opposite. So in this case, we'll do base, but of course, if we had the base in the Erlenmeyer flask, we would use an acid. And this is called the titrant. Titrant, we'll do it in blue. Titrant. T is the known amount, it's in the burette. A teeny mnemonic here is, for me, D is like don't know, right? And T is I do know. I don't know if that's helpful, but knowing that the D is dunno helps me to remember that that's the unknown amount. So we have our titrant here. Now, how will we know when we're neutralized? Well, that's why we have indicators, which we talked about in the previous video. What we'll use is we'll put an indicator into the solution along with our titrand. And what we'll do is we'll watch for the color change. So when that indicator changes color from red to blue, or from red to yellow, or from colorless to red, then we'll know that the reaction has neutralized and we'll be able to plot it on our titration curve. So you set this all up and you have a known concentration. Let's just use some numbers here so that we can practice as we go. So let's say that we have 10 mole per liter of NaOH in our burette. That's our titrant. And let's say that we have 100 milliliters down here with our titrand, 100 milliliters of HCl. So we know the volume, but we want to know the moles. We want to know how much acid we have. So what we're going to do is you're going to very slowly, you might have done this in laboratory, you very slowly drip, drip, drip our titrant, A-N-T, into our titrand. Very slow and careful, right? Because we want to have exact volume concentrations. And as we add more base to that solution, the pH is going to increase. So as we drip, we're going to see that this is going to start to go up. And then as that goes up, at a certain point, it's going to go up really quickly. And that's going to be where we have our neutralization reaction. Because once that happens, our pH changes very quickly as our molecules start to lose protons to the solution. And then at a certain point, it's going to flatten back out. This is our end point. And so when we see that indicator, we want to make sure that that indicator changes colors somewhere in this steep part of the range. Let's go ahead and say that this is 8 up here and 4 down here. So we might want to use a litmus solution for this guy, for this indicator, litmus, since our litmus will change colors once we hit 8.3. And so we'll know that that endpoint has happened. And so what we do is we say, as soon as we see that endpoint, we stop. We stop dripping. So as soon as you see that color change, you turn off the little nozzle here and make sure that it stops dripping. And then you see how much volume you used up. So let's say that we started here at 100 milliliters and now we're at 70 milliliters. So how much did we use up? We used up 30 milliliters. And that will also show up here when we graph it. Our volume of our titrant that we use up is on the x-axis. So let's say that it's 30 milliliters. Let's say, we started with 0, kept moving up, and then our center point here is 30 milliliters. So this sharp point right here, where it goes up steeply, and we turned it off right at the end, this is called the equivalence point. And the equivalence point is where, I'll go ahead and rewrite it over here on the side. The equivalence point is where the moles of acid will equal the moles of base. So awesome for us because that's exactly what we're looking for. So now we know, okay, if we can figure out the moles of base, the moles of our titrant at the equivalence point, then we'll also know our moles of our acid. So let's do that math together. So we know that we had 10 moles per liter of NaOH, our titrant, TRA and T, right? And then we know that at the equivalence point, we put in 30 milliliters. So we'll do a quick conversion here. 30 milliliters, milli is 10 to the negative 3. 30 is 10 to the 1. So multiplying that, it's 3 times 10 to the negative 2 liters. We have to do that because we're in liters for our molarity. So now we multiply 10 molar times 3 times 10 to the negative 2 liters. The liters will cancel. And we end up with 10 times 3 is 30. At 10 to the negative 2, we can just move that over. 3 times 10 to the negative 1 molar, or 0.3 molar. You can double check with your calculator to prove that's true. So this is how many moles of NaOH we have at the equivalence point. And by definition, the equivalence point is the neutralization reaction. It's where the moles of acid equal the moles of base. So how much acid do we have then? Well, we have 0.3. So we have 0.3 moles of acid because we didn't add any more acid, right? We just left it as it is. So as we're dripping, that's how much we had. So now we know we have 0.3 moles of acid, or H plus concentration, because we know based on our stoichiometry here that HCl, when it ionizes, is H plus and Cl minus. So if we have 1 mole here, we'll have 1 mole here, right? So we know how many moles of HCl we have, which is 0.3. Now, what if I wanted to get the molarity though? Often we are working in concentration and we would want molarity. Well, that's why we needed to know the volume of our titrant, because we needed to know how much we started with so that we can calculate our molarity, because molarity is moles per liter. So all we have to do is divide our 0.3 moles by liters here. And again, we're going to have to convert because this is in milliliters, which is not okay for our molarity. It's got to be in liters. So milli, 10 to the negative 3, 100, 10 to the 2, 2 plus negative 3. When we're multiplying exponents, we add them, negative 1, right? So 10 to the negative 1. So rearranging that math there, 0.3 moles, or 3 times 10 to the negative 1 moles, over 1 times 10 to the negative 1 liters, because that's the same thing as 100 milliliters. These guys cancel. So it's going to end up being 3 moles per liter, or 3 molar for our acid. So that's why and how we use titration curves, is we have a known volume but an unknown concentration of either an acid or a base. If it's an acid, we're going to put a known amount of a known concentration of the base in the BRA. Then we're going to add an indicator so that we know, okay, when it's changing colors, that's when we turn it off, because that's when the end point has happened, when we finished our neutralization reaction. You always want to choose an indicator that matches with your titrations. Next up, we're going to talk about different types of titrations and which indicators we would choose for those types of titrations. But we'll put our indicator in so that we know when it's going to change color. Then we very, very slowly drip, drip, drip that titrant, in this case that we just did, our base, into our acid, that our constant amount of acid, and then we slowly plot the pH change as it's going. So again, this can be done through a machine, or you can be taking different volumetric measurements here, and we can kind of plot out as we're adding in that volume. Then, as soon as that indicator changes colors, we stop adding in our titrant, our base, because we've reached the end point. And we're able to say, okay, that volume at our end point, that volume is what we have at our equivalence point, because it's a nice straight curve here. It's a nice steep curve. And when we have that volume, we can multiply that volume times the molarity of the titrant, right, of our known amount, and that will get us our moles of our titrant at the equivalence point. Moles of our titrant, moles of our base in this case, will equal moles of your acid, and that's sometimes all you need to know. This is how many moles of acid we had. But if you did need to know molarity, you would just divide by liters. And then of course, with stoichiometry, if you wanted to know grams and you have moles, well, you would just multiply by the molar mass. And that would be something provided to you in your question, or you would be given a periodic table and you could calculate that molar mass, and that would get you the grams of your acid. But we always start with the same steps. Take the known amount of our titrant, multiply by the volume of the titrant at the equivalence point. That's going to give you a 1-to-1 ratio. Now remember, this is assuming, and this is generally true, this is assuming that we have a 1-to-1 molar ratio between our acid and our hydrogen ions. If we do have a 1-to-2 molar ratio, for example, if we used H2SO4, then we would need to do some stoichiometry, because for this guy, we would have 2 H+ ions, right? So the calculation here, what this volume of our base would be, we would have to divide by 2. Divide by 2 because it's twice as much base as we had acid, right? 1 OH- for every 2 H+. So whatever this volume is, we would have to divide by 2 to get to the molarity of just 1 mole of HCO, H2SO4. So if you have more hydrogens, you divide by that number, right? And that's going to give us our concentration. But most of the time, it'll be a 1-to-1 ratio. If you have more than one of our ion of interest, in this case hydrogens, you just divide your number that you got from your titrant by that number, in this case 2, and that's going to get you your concentration. Most of the time though, it's really going to be a 1-to-1 calculation because we're going to have most of our acids being a 1-to-1 calculation when we use titrations and titration curves like this. Before we get into the different types of titrations and the indicators that are good to use for those titrations, I'm Amanda Brem, and I've been coaching pre-medical students on their MCAT journey since 2019. Please remember to subscribe to this channel for more videos on MCAT content, test-taking strategies, and mental fitness tips to help you perform your best on testing. And if you'd like to join me in my next live online 6-week MCAT cohorts, please check out the link in the caption below. All right, let's dive back in. Our first type of titration is if we have a strong acid with a strong base. Now, I am going to draw all of these as if our acid is our titrant, our unknown, because if our base is our unknown, we're going to kind of draw it downward since we would start at a high pH. So I'm just going to draw it again under the assumption that our acid is our unknown. And I just want you to know if our base was our unknown, we'd start with a high pH because we would start with our base, right? So we would kind of just look the same, but in reverse. So for a strong acid, our pH is on our y-axis, and then the volume of the titrant So on our x-axis, as we do a strong acid, strong base titration, we're going to start at low pH and then go up, go all the way through, and then have a nice sharp increase right around that neutral pH range, and then kind of flatten out right around 9 or 10. We start to see our end point here. So for a strong acid, strong base titration, we want to make sure we choose an indicator. Indicators that will change color right at the end of our equivalence sharp increase, right? Our equivalence point here. So this is going to be changing color anywhere after 7 in the 8 range. Honestly, with a strong acid, strong base, we could pretty much use any major indicator because we're starting so low and ending so high that we're definitely going to get a color change somewhere. But we often will use phenolphthalein because it changes color right around that 8-ish range, right? So less than 8.3, greater than 10. That's where we're changing. So we'll definitely see that change happen right at that 8.3. But we really could use anything. We could use litmus. We could use bromoethyl blue, which is a 6 to 7.6 range. So for strong acid, strong base, you can pretty much choose your indicator, choose your poison, and it will probably work. For the rest of these though, it is going to matter whether or not we're using a certain type of indicator. So next up, let's say we still have a strong acid that we're working with, but now we have a weak base, a little less good of a base. Well, what's going to happen if we have a strong acid or weak base? I want you to kind of visualize, we're probably going to stay in a lower pH range, right? We're going to stay with that stronger component. So our curve, 2, 4, 6, 8, is really going to top out around 7. It's not going to really go all the way up to our high end range here. So it's going to be kind of like a smushed shorter curve. Okay, so that means that we want our indicator to be more acidic because we are under that pH of 7. So our methyl red may be a good option. It has a range right where it changes color right around 5, the pH of 5. And so that would be good. Anything kind of under 7 is going to be better for our strong acid, weak base. And the stronger the acid, the lower we want our indicator to change color. Now, one note here, as we're talking, when I'm using these numbers 8.385, what they're actually referring to is these indicators pKa. We've talked about pKa before. pKa, remember just briefly, is our negative log of our Ka, and our Ka is our acidic reaction, right? So when methyl red, let's just say our protonated methyl red, goes through our acid reaction, it's going to donate its proton and become methyl red anion, all right? And that equilibrium constant, that Ka, is what we're referring to, our pKa. So the lower pKa, right, the more acidic, more acidic. So really what we're saying here is we want a more acidic indicator if we're using a strong acid, weak base titration. Okay, so just kind of connecting those dots here. When we're talking about indicators, the best thing to do, I'll put our rule up here now before we go through the rest of these. Our pKa of our indicator should be close to our equivalence point, really within 1, right, of our end point. So right around here, wherever that is on our curve, that's what a good indicator will be. Okay, let's keep going to finish out our pattern here. So our next titration is now going to be a weak acid, but a strong base. In this case, we're going to see it be higher, right? The base is going to win in this particular titration. So we're going to start higher. So because our weak acid that we're titrating is not going to have as low of a pH. And then we're going to end up much closer to our basic range rather than our acidic. So it's kind of going to be upshifted here for our weak acid, strong base. So again, a good indicator here will have a pKa of greater than 7. So phenolphthalein is another good one. You see phenolphthalein a lot. It's a very common indicator here. But another one might be thymol blue. You might have used that one before as well. Both of these have pKas of greater than 7. They're going to change color above a pH of 7. And so that would be really good for a weak acid, strong base. Now our final one, of course, we can see the pattern here, right, is going to be a weak acid, weak base. And in this one, it's going to be around 7 again. So we're going to want to use that same kind of indicators around 7. But in this case, we're going to flatten out the whole curve. We're going to start higher, but end lower. So it's really going to be like a nice little gentle bloop curve here. It's not going to have a very sharp equivalence point. It's going to hover right around our 7 here. And again, relatively speaking, if one of them is stronger, it may win slightly, but it's going to be a much narrower range for us to work with. So in terms of indicator here, not only do we want it to cross over and have a pK, have a change in color right around 7, we also want it to have a pretty small range. So a good option here would be bromothymol blue. It's not thymol blue, bromothymol blue, different thing. You know, similar sounding, similar structure, but different, because this guy has a pK of right around 7.3. So that means it's going to change color right in this range. Probably going to be our best bet here for a weak acid, weak base. So again, for most parts, depending on your classes, depending on your tests, you probably don't have to memorize indicators, but check out their numbers and then know what we're looking for. So quick review, strong acid, strong base, pretty much anything will work as long as it changes color somewhere between like 4 and 10, right? So anywhere having a pKa of anywhere between 4 and 10 is going to be fine. Methyl red or something like it for strong acid and weak base. So if you have strong acid, weak base, you want an indicator with a pKa of less than 7. Weak acid, strong base, you want an indicator of greater than 7, right? To go with your strong base. And then weak acid, weak base, we just want one real nice and close to 7. So picking an indicator that will change color right around a pH of 7. Okay, and those were the 4 different types of titration curves and the indicators that would be best to use for each one. Hope that video is helpful, and I'll see you in the next lesson.